column, keep your eye on it, because later today, that ion exchange column is going to be hard at work helping me purify my protein. So ion exchange chromatography is a form of protein chromatography, which is a technique that we can use to separate proteins in order to help purify them or analyze them. And so how it works is that you have these columns filled with these little beads called resin, and you can have different types of resin with different properties that can separate proteins based on things like their size, or what we're going to talk about today, their charge. And so ion exchange chromatography separates proteins based on their charge using resin that is charged. And so you can use an anion exchange resin if you have a negatively charged protein. In that case, the resin is going to be positively charged, so your protein is going to stick to it. If you have a positively charged protein, then you use a cation exchange column, which has negatively charged resin, so the positively charged proteins stick to it. Because different proteins have different combinations of amino acid letters, and some of these amino acid letters can sometimes be positively charged and others can sometimes be negatively charged, different proteins are going to have different charges. And we can use ion exchange chromatography to take advantage of these differences in charge, because it's going to make them stick differently to columns. And so the more positively charged something is, the stronger it's going to stick to something that's negatively charged. So the stronger you're going to stick to one of those cation exchange columns. The more negatively charged something is, the more it's going to stick to a positively charged column. So the more it's going to stick to one of those anion exchange columns. So you're going to have proteins stuck. If you take a mixture of proteins and you put it through one of these columns, you're going to have the proteins, these proteins are going to be stuck to different extents. So what we can do is we can add salt. So up here I have a high salt and a no salt buffer, and what I do is I have this ACTA, so this machine that's controlling the flow of the liquid, so like the flow of the buffer, so the pH stabilized salt waters, you can have it flow through the columns, and then it's going to come out and we'll see a peak on here, because as it comes out of the column, which we say it elutes, then it's going to go through a UV detector before it goes into this fraction collector, and then we can look on the chromatogram and see where the peak comes out, because proteins absorb this UV light. And so we can have the ACTA put like a line A and a line B in, and then it has these pumps that are going to mix them. So we can make a gradient of salt. And what this salt is going to do, because salt is made up of a positive part and a negative part, so like sodium chloride would be a sodium and a chloride ion. And so those ions from the salt are actually going to compete off the protein from the columns. And the more your protein is stuck, the more salt it's going to take to push your protein off. So you'll see that things that are less stuck will come off sooner, and things that are more stuck will come off later. That one was already pretty pure, so there wasn't too much to see in that peak. Because we're typically using this, I'm using it as a second purification step, so I already done like a capture step, so where I use the specific affinity chromatography. I express my protein with a little extra bit on the end, a tag that is going to let me help purify it with affinity chromatography, so with a strep tag or a his tag or that sort of thing, and more on that in other posts. But because you're using something super specific about that protein in that capture step, you get rid of most other stuff. But there's still some stuff lingering, and so this is where the ion exchange chromatography can come in. In addition to anything that non-specifically stuck to that affinity column, you can also have things like if you added a protease to cut off the tag, and now this can help you get rid of it. Furthermore, after you do this, then you can do a further polishing step with the gel filtration, which is one of these bigger columns, and if all goes well, I'll be using that really, really big one tomorrow. In addition to helping purify it, it'll also get rid of that extra salt, because you're competing off. If your protein's really stuck, you're going to have to add a lot of salt to push it off. And so what determines how stuck your protein is? Well, the sticking is going to depend on positively or negatively charged regions of your protein. So proteins are made up of these amino acid strings, and they have different combinations of the positive ones and the negative ones at different points. So it's actually these like kind of more like regions of a protein that are going to be sticking to the column. But overall, we can predict whether a protein is overall positive or overall negative. And this is typically what we start with when we're trying to decide whether to use an anion exchange column or a cation exchange column. And this charge is going to depend on the protein's PI, or its isoelectric point, the point at which it is electrically neutral, so the positives and the negatives cancel out, and it's going to depend on the pH. So in order to understand all of this, we need to step back a little and talk about this PI, the relationship between PI and pH, as well as how it contributes during ion exchange chromatography. So basically, if you're below the PI, your protein is going to be more positively charged on net. If you're above the PI, in terms of pH, your protein is going to be more negatively charged on net. So you need to use a pH that is going to make your protein the charge that you want, but you typically don't want to make your pH like crazy. You can actually elute the protein off by changing the pH, but typically we don't really want to mess with the pH because our protein's typically happy at a pH where it normally works in. So typically I use a pH somewhere between 7.4 for some proteins and 8 for the protein I'm doing today. And so I want it at the pH of 8, my protein is going to be positively charged because my protein has a predicted PI of over 9. And so at a pH of 8, it would be positively charged, and so I'd use the cation exchange column. So those are the basic concepts, and let's talk about where all this is coming from. And now that I've given the kind of overview and just kind of rambled a lot, let's look in a little more detail. First, let's clear up some terminology, starting with the simpler terms. So ion. An ion is just a charged particle. So we can talk about cations, which are positively charged, and anions, which are negatively charged. A salt is just a neutral combination of positive and negative charged particles. So for example, sodium chloride, you have a sodium ion and a chloride ion. And when you dissolve a salt, what actually happens is that those are going to dissociate, those are going to come apart and give you individual sodium and chloride ions. And this is how you're able to have those salt ions competing for the spots on this resin. So now let's get to the trickier terms. We need to distinguish between pH, pKa, and PI. These terms are all related and they're all different though. So with the pH, we're dealing at the level of the entire solution, so at the environment that the protein is in. With the pKa, we're dealing with individual amino acids. And then with the PI, we're dealing at the protein level, so the combination of all those amino acids. And so the pH is just a measure of the free proton availability. And it's an inverse log, so the more protons there are, the more acidic a solution is, the lower the pH. The fewer protons there are, the higher the pH and the more basic or alkaline a solution is. I like to think of it kind of like the pH is kind of a measure of proton jar fullness. So if we think of a kind of Cookie Monsters, then the pH is how full that cookie jar is. And then we have acids and bases, which are taking, the acids would be giving protons, so giving cookies to the jar, and the bases will be taking protons, so taking cookies from the jar. And if you imagine that different acids and different bases have different greedinesses, so if something's a really strong acid, it's going to give up its cookie even if even if the jar is really full. So even at a low pH, you would have this acid would be deprotonated because it will have given up its proton. But if you have something that is more greedy, it wouldn't want to give up its proton. But maybe if there's barely any in the jar, maybe it'll be like, okay, I'll give in, I'll give you my cookie. And so it would be more likely to be positively charged unless the pH is really, really high, meaning that the proton jar is really, really low. So of course, these molecules aren't really acting like Cookie Monsters and they don't have feelings like that. But if you imagine just from a probabilistic standpoint, if something has a weak hold on the proton and it lets go of the proton, and we need to find a new proton in order to grab on again, even if it was a fleeting interaction, if there's so many protons around that as soon as it lets one go, another one grabs right on, then you're still likely to find it protonated. So at a low pH, you're still likely to find things protonated, even if they have they're very weak acids. Whereas at a high pH, if you have a weak hold on that proton and you let go, you're less likely to run into another one. So you're less likely to pick one back up. So at a low pH, you're more likely to be protonated, and at a high pH, you're more likely to be deprotonated because there's fewer protons around. But where that limit is between like more or less likely to be protonated is going to depend not only on the pH, but it's actually going to depend on the pH at which you kind of like cross the line between being more likely to be protonated and more likely to be deprotonated is called the pKa. And this pKa is going to differ between different acids. So above the pKa, the proton, you're going to be more likely to be deprotonated, and below the pKa, you're more likely to be protonated. So in the situation of a protein, what we actually have is we kind of have chains of Cookie Monsters, and some of these are really greedy and some of these are really generous. And so it's the combination of these amino acids as well as the pH, so how full that cookie jar is, that's going to determine the charge of the protein. So the pKa is the value at which half of it is more likely to be protonated and half of it would be deprotonated, or there's like kind of like a 50-50 chance that it would be protonated. We can look at the pKa of something and we can look at the pH and predict whether that acid is more likely to be in its conjugated acid form, so it's protonated, or its conjugate base form, it's deprotonated. And so you can then compare the pKa to the pH in order to see what it's more likely to be. And because it's a log scale, for every 1 point change in the pH, you're going to have a 10-fold more or less of the protonated or deprotonated form. So we can do this for the amino acids that have the ability to act as acids or bases. So the terminology kind of gets confusing because we talk about them, their name, we give them their kind of names or how we refer to them in their neutral form. So we call acidic, aspartic acid, and glutamic acid, even though they're normally existing in their conjugate base form. So they have a pKa around 3.7 for aspartic acid and 4.3 for glutamic acid. And so in our bodies, when we have a pH around like 7.4 or so, we're going to have them predominantly in this negatively charged conjugate base form, because we are far to the right of their pKa. However, because in their neutral form, they were acting as an acid, we call these amino acids acidic. And if a protein has a negative charge overall, we tend to call that protein acidic. On the other side, we have amino acids that can be positively charged. We call these basic. So these are histidine, lysine, and arginine. So we call these basic because in their neutral form, they can act as a base and accept a proton and become protonated. And so in their positively charged form, they've already acted as a base and now they're the conjugate acid. And so if we look at lysine and arginine, they have really high pKa's. So if we go over here, we're going to be way to the left of where they are. And so they're going to be predominantly protonated. If we look at histidine, it had a pH of around 6, so we're actually going to be over here. So we're going to be majority deprotonated, but there's still a fair amount of the protonated form. And so it can kind of go back and forth a lot more easily than the other ones. And so histidine plays a lot of important roles in proteins and especially in enzymes and catalysis and all sorts of really cool stuff. But this is looking at the amino acids in alone. And so typically too, these pKa's are determined for these amino acids, just like free and alone. But in our protein, we have a whole chain of them, and how they're going to act when they're in a protein is also going to be influenced by what's around them. And so you can have kind of like local pockets where the pH is kind of different. You can have other amino acids kind of pulling on the protons or making them more likely to act one way or another. And so with the pKa's, when they're together, are going to be a little different. But overall, you can actually say, okay, well, if I take into account the combination of amino acids, the pKa of each of these amino acids, I can determine this value called the pi, or the isoelectric point, which is going to tell me the pH at which the positive and the negative charges cancel out. And this is going to be different for each protein because different proteins have different combinations of amino acids. And this is the basis of ion exchange chromatography, is these differences in a protein's isoelectric points. Well, it's actually technically more of because the binding is actually occurring in kind of regions or pockets on the protein, you can actually have a protein that's overall positively charged still be binding to a positively charged column because of the little patches. This is not going to bind as well as it would to a negatively charged column. What I use is this tool called XBase Prop-Param. This is a really great tool, and I talked about it more in my resources video, I think. But basically, you can stick in either the name of the protein, or it's some sort of identifier from like Uniprot or something, or you can actually paste in your own amino acid sequence. So this is really great if you're making mutations to the protein, you're making truncated conjugates and that sort of thing, and you want to see how that exact protein is going to behave. So it gives you a lot of information. It gives you things about the extinction coefficient too, if you want to kind of convert for UV. It gives you the number of amino acids, the molecular weight, and the theoretical PI. So this is the protein I'm working with today, and so it has a theoretical PI of 9.32. And remember, it's theoretical because these amino acids are going to, when they're in the context of a protein, it's not like you can't extrapolate from the individual amino acids exactly to how they're going to behave in the protein state. But it has a theoretical PI of 9.32. So in this graphic, I have it as the pKa, but you can also imagine the same thing with the PI. And so the PI tells us where we draw the 50-50 line at the protein level. The pKa is telling us where we would draw the line at the amino acid level. The buffer that I am using has a pH of 8. So I'm going to be to the left of the pKa, and so my protein is going to be predominantly in the positive state, and so I say my protein is fairly basic. So because it has more of those basic amino acids, and it's going to be more in the positive state. So what I want to do is I'm going to do a cation exchange chromatography. So I'm the ion is, it's always confuse me, and I always have to think about it a little. But what they're talking about is the thing that's exchanging, and so your protein and the salts are going to be exchanging for spots on the column. In the equilibration, we put some salt on the column. We put some, so this will be like your sodium, or in my case, potassium ions. They're going to bind to the column, and then you're going to have your proteins flow through. The positively charged proteins are going to stick to the resin, and they're going to kick off some salt when they do that. So your protein is basically exchanging for this cation, for this other cation, for this salt cation on the resin. Then what you're going to do is you're going to wash things off. And now when you increase the salt, you're basically adding competitor. You're adding more cations that are going to then push off your protein. They're going to exchange for your protein. When they exchange for your protein is going to come out. If you have an anion exchange column, now you can do the opposite. And so here, though, you can, because salt has this positive and this negative, you can use the same salt in both cases, because it's just a different part of the salt that's going to be binding. Because remember that when you put this in water, the positive and the negative parts, so the cation and the anion are going to separate. And so here it's the anion that's going to bind and exchange. So the positive resin is for anion exchange, which you use for negatively charged proteins, which you use typically above the protein's PI, if your pH is above the PI. For cation exchange, you have positively charged protein, which is going to bind to negatively charged resin, and you're using it when the pH is below your protein's PI, meaning that there's lots of protons available, so your protein's more likely to be positively charged. The stronger it's stuck, so like the least oppositely charged protein tends to come off first, and then the most oppositely charged protein is going to come off last. But know that predicted PI might not always be exactly accurate in terms of what the protein's actual charge is, and also that because it's depending on like patches of your protein, you can have your protein bind to both types of columns, and things might not always come off in the order that you predicted. You can alternatively elute proteins off by changing their charge, so by changing the pH. Instead of competing them off, make it so that they don't want to stick as much. But we typically don't want to change the pH too much, because the protein tends to be happiest at the pH that it's used to. And what you also want to avoid being at the isoelectric point. So being at that PI where it is net neutral. When a protein is neutral overall, this tends to be its least soluble form, because water has positive and negatively charged parts. And so water likes things that have positive and negatively charged parts. If there's fewer positively and negatively charged parts, or if it's overall neutral, then there's less of these favorable interactions between the water and the protein. And so then it's going to be least soluble, because the protein being soluble means that you have a full water coat. And if the water doesn't want to hang out with you, now you can't get that water coat. So you're going to clump up and combine with other proteins. Columns with an S are cation exchange ones, and the ones with a Q are the anion exchange, at least for these is a mono Q. There's also like a high trap Q. So I think that the mono Q is supposed to give you slightly better resolution and stuff. Here's where the high trap Q is. You can hook these up back to back if you have more that you need to do. So what you do in one of these runs is basically you equilibrate your column, so you get it in the buffer that you want it to be in. And so typically this is some sort of low salt buffer. So often what you're going to do is you're going to do something from like a 100, you'll do like a 100 millimolar salt or something, and then you go do a gradient up to like 1 molar. And so, but you want to equilibrate it at this low salt concentration to basically make it so that there's not much competition to get on, but you don't want it to be zero competition, because you want there to be a little competition, so not just anything combined, and because proteins are not going to be happy if you don't give them any salt. And so this is another thing. So when you start your purification, you want to actually dilute your protein to that concentration that you're equilibrating your column at. So typically what I do is I actually have I do my strep elution, so my affinity chromatography, and then I do the TEV cleavage. So I cleave off the tag. Now I don't have that tag. I'm going to take advantage of the natural properties of the protein, starting with its charge. But because I am doing the affinity chromatography at a higher salt concentration, so I have like a 200 millimolar salt, I need to dilute it down to that starting concentration. So often when you're doing an affinity chromatography step, you're using a high salt, but because you might have used the high salt to help with the lysis, and because proteins tend to be often are more stable with the higher salts, and because it makes it harder for things salt makes it harder for things to stick, and so it makes the less non-specific binding to your column. So it's good to have a higher salt concentration for the affinity chromatography step that we were doing before. But now we need to dilute it down so that it has a chance to bind to the column, because if there's too much salt there already, there's going to be too much competition and it's not going to bind. So you want to dilute it down. And so typically what I do is I actually use like a graduated cylinder, and I have it filled with like 50 mils. I normally do my elution from the first one in 50 mils, and then I mix it with 50 mils of the no salt buffer to get it down to the starting concentration, so that it's at the same level as my buffer salt level as my buffer when I put it on. When you're doing that dilution, so if you haven't worked with the protein before, you want to make sure that it's actually going to be okay in that lower salt concentration. So sometimes if you decrease the salt, it'll actually crash out. So it'll like precipitate. So the salt helps kind of provide interactions for the protein. And if it can't get those interactions from the salts, then it might try to get them from other protein molecules, leading your protein to kind of clump up and precipitate out. So what you can do to test this is take a little sample and dilute just that little sample. So take a mil or something and just dilute it to the concentration that the rest is going to be at. And then if it precipitates out, you know that you can't go that low in your salt concentration. You might also find that out the hard way when you're doing dialysis. So dialysis is basically this method where we put a protein in like a little membrane pouch, and then we stick it into this buffer that doesn't have the thing that we want. So it has the components of the buffer that we want, but not those that we don't want. And we choose this membrane of our little pouch so that the protein can't get through. Our protein's too big to get through, but the little things like the salts can. And so then we can dialyze it out. And so this is an alternative way too, if you need to lower your salt concentration before going onto the column and you don't want to dilute your sample, because when you're diluting your sample, then you have more sample going onto the column and your run's going to take longer and stuff, although dialysis also takes a really long time. But there might be other things in your buffer that you don't want going on in your purification, so you can get rid of them with dialysis. Wash the column, so you basically just let things come off that didn't stick very well on there, and then do an elution. And you can do this by like mixing these buffers, and so you have like a no salt buffer and a high salt buffer, and then these buffer mixers are going to mix them together. You can have them mix them together in this gradient form where you do like a linear gradient, or you can do it in a stepwise elution. If you know what salt concentration is required for your protein, you can do this stepwise. I actually do this to help purify my protein because I have this protein that some of it binds to RNAs, like a fraction of it is already bound to RNA. Some of it's not. RNA is negatively charged, so it's going to make my protein less positively charged. And so I can do this stepwise gradient elution based where I can get off the stuff that's bound to RNA at this lower salt concentration and then a higher salt concentration to get off the stuff that's not bound to RNA. So it's a higher charge. And then I do a super high salt because you want to wash off the column to make sure that anything that's stuck on there is going to get off before the next person goes to use the column. One time, someone hadn't washed the column and then all this weird stuff came off and it ruined my stuff and I had to rerun my stuff. So you want to always wash your column at the end. I also, what I do is after I do the run, I do a high salt wash. I do it like flow up through the column at a slow rate. So I do like 0.5 mils per minute as opposed to like the run goes at like 4 mils per minute. And I do 0.5 going up for like a column volume. But anyway, that's just a technical note. And then you can collect fractions. So these fractions are going to go when the thing goes off the active, it goes through this UV detector, and then it's going to go to the chromatograph, and then this is going to correspond to the fractions in this fraction collector. So typically for one of these runs, you'll have like a 96 well block, and you can collect different fractions. You can do smaller fractions if you want to be able to make sure you separate things better, like so that if you had a peak that were close together, you could isolate the different peaks. But then you also have to collect a lot more, you have to combine a lot more fractions at the end. So if you know your protein really well, you can set up the protein. If you've done this purification a lot of times, you can set up bigger fractions if you know exactly where it's going to be and that you don't need to worry too much about it. But for something that you've never worked with before, I typically do like a gradient elution with fine fractions, with little fraction sizes. So my workflow is typically something like this, where I use affinity chromatography. I express my protein with a tag on the end. I typically a strep tag or a his tag, strep most of the time because I'm doing insect cell expression and strep tag works well for that. And then I compete it off, I cleave off that tag. Now when I don't have the tag, then I take advantage of the charge. I do my exchange chromatography. And then I do my size exclusion chromatography. And so hopefully at the end, I'll have, I'm getting rid of all of these extra proteins and have a nice pure band, which is corresponding to the pure protein. When your protein comes off of the ion exchange column, it's going to be coming off with a lot of salt that you use to push it off. And so often you want to get rid of this salt. So even if you don't care about making the protein purer, maybe your protein's already really pure, sometimes size exclusion chromatography can be a good way to just get rid of that salt. Because the smaller things are going to have, the smaller things go through all these tunnels, they're going to take longer to get through. And so when you equilibrate your column, all like the little things like the salts and stuff, those are really little. So those are going to be in here. And so the buffer that is in the column is going to come out with your protein. And so your protein is going to come out, your protein is going to elute in the buffer that the column was equilibrated in. And so if that buffer had a lower salt, well, now your protein is going to come out in that lower salt as well. An alternative is dialysis. But dialysis is going to take some time, but that's just dialysis is what we saw before. But the thing about dialysis is at least then you don't have to concentrate your protein and run it through another column.
So in order to do size exclusion chromatography, you're going to concentrate your protein down. To do this using these like centrifugal filters. And so that's typically what I'm doing after my mono S is I'm collecting those fractions and I'm concentrating them and then doing gel filtration. But you can also get rid of that salt using dialysis. So with a little pouch or a little something like this, depending on the volume that you have. If you're having problems with your ion exchange chromatography. So typically the first place that we start when we're determining what type of column to use is by looking at the PI and making sure that the pH that we want to use is going to be appropriate for that, for being at a charge state in, for given that our protein has that predicted PI. And so if you had a low PI, you would want to use anion exchange, and you had a high PI, you would want to use cation exchange. If you're doing it and it's still not binding, you can do things to try to increase the binding. So if you have a low PI, basically your protein is going to be negatively charged. And so if you increase the pH, you're more likely to be more negatively charged. But remember, you have to be careful when you're doing any of this because you don't want your protein to become unhappy. Alternatively, for on the other side, if you have a high PI, so if you're doing cation exchange or protein's positively charged, you can increase the chance of it being more positively charged by lowering the pH. In either case, if you decrease the salt, you're decreasing the amount of competitor and making it more likely to bind. And so if you're having problems with binding, these are some things that you can try. If your protein is you're still having issues, sometimes I actually had this protein and its predicted PI was, I don't remember which direction it was, but it seemed like it should bind one column, but it wasn't binding. And so I hooked up you can connect some of these columns. So I hooked up an anion exchange and a cation exchange column back to back, then ran it through and looked to see where the protein was stuck. If your protein is still not sticking, you can also try hydrophobic interaction chromatography, HIC, which is actually doing the binding based on the hydrophobic interactions, which if your thing isn't like in the charge interactions, maybe the hydrophobic interactions are something that you can go after. So hope this helps and good luck with your ion exchange chromatography.